Competency number 2, objective. After completing this competency, the student will be able to size CSTRs and PFRs given the rate of reaction as a function of conversion and reactor volumes for reactors arranged in series. This competency will have 7 parts. In part number 1, we will see the definition of conversion and we will define the batch reactor design equation. In part number 2, we will go to the design equation for flow reactors, CSTRs, PFRs, and PBRs. In part number 3, we will go to some application of the design equations for continuous flow reactors. We will see reactors in series and the concepts of space-time and space velocity. In part number 4, 5, 6, and 7, we will resolve some problems. Definition of conversion. In defining conversion, we choose one of the reactants as the basis of calculation and then relate the other species involved in the reaction to this basis. In virtually all instances, it is best to choose the limited reactant as the basis of calculation. We develop the stoichiometric relationships and design equations by considering the general equation A of A plus B of B will give us C of C plus D of D. The capital letters are the reactants and the lowercase letters are the stoichiometric coefficients. Let's take species A as our basis of calculation. So we divide the reaction expression by the stoichiometric coefficient of species A. So we will have A, the reactant A, because the coefficient A divided by the coefficient A is 1, plus the coefficient B divided by the coefficient A times B gives us the coefficient C divided by the coefficient A times the reactant, the product C, plus the coefficient D divided by the coefficient A times the product D. In this way, we put every quantity on a per mole of A basis, which is our limited reactant. To quantify how far a reaction proceeds to the right, or how many moles of C are formed for every mole of A consumed, we define a parameter called conversion. The conversion, in this case represented by the letter X, so the conversion XA is the number of moles of A that have reacted per mole of A fed to the system. For irreversible reactions, the maximum conversion is 1. That means that all the reactant goes to product, which means complete conversion. But for reversible reaction, the maximum conversion is the equilibrium conversion. So X maximum is equal to Xe, which is the conversion at equilibrium. Batch reactor design equations. In batch system, the conversion X is a function of the time the reactants spent in the reactor. That means we put the reactants inside the reactor and we leave them for some amount of time. The more time they are spent inside the reactor, the more conversion will take place. If Na0 is the number of moles of A initially in the reactor, then the total numbers of moles of A that have reacted after a time t is equal to Na0 times x. So we will have that moles of A reacted is equal moles of A fed times the conversion, which is mole of A reacted divided by moles of A fed. We can see here that mole of A fed in the right side of this expression will be eliminated, and we will have mole of A reacted in both sides. Then, if Na is equal to moles of A in the reactor at time t, and Na0 is equal to the moles of A initially fed to the reactor at time t equals 0, Na0 times X will be the moles of A consumed by chemical reaction. And the number of moles of A in the reactor after a conversion X has been achieved is Na equal Na0, which are the initial moles of A, minus Na0 times X, which is consumed of A, so they will be Na0 times 1 minus X. And the mole balance on species A for a batch system, we must recall that is dNA divided by dt equal to Ra times B. And this expression is valid if the reactor volume is constant or not. A is disappearing, therefore we multiply both sides of last equation by minus 1 to obtain the mole balance for the batch reactor in the form minus dNA divided by dt is equal to minus Ra times B. If we are talking about the rate at which a reactant is consumed, it will be negative. And if we are talking about the rate a product is appearing, that will be positive. In this case, A is disappearing, so his rate will be minus Ra. So the rate of disappearance of A minus Ra in this reaction might be given by a rate law such as minus Ra equal K, the concentration of A times the concentration of B. For batch reactors, we are interested in determining how long to leave the reactants in the reactor to achieve a certain conversion X, because we need to remember that for batch reactor, we are interested in the time we leave the reactants inside the reactor and not the volume by which the reactants flow through, like in flow reactors. To determine this time, we write the mole balance dNA divided by dt is equal to Ra times B in terms of the conversion. So if we differentiate Na equal to Na0 minus Na0 times X, which is the expression for Na at any time, and we differentiate this expression with respect to t and remember that Na0 is constant, so we will have that dNA divided by dt is equal to 0 minus Na0 times dx divided by dt. Then minus Na0 dx divided by dt is equal to Ra times B. So, for batch reactor, the design equation in the differential form will be Na0 divided times dx divided by dt is equal to minus Ra times the volume B. For a constant volume batch reactor, the volume B will be V0. There is no change in the volume. And the equation dNA divided by dt equal to Ra times B can be rearranged into the form 1 divided by V0 times dNA divided by dt is equal, we will put V0 inside the differential, so it will be equal to dNA divided by d0, all that divided by dt. But Na divided by V0 is the concentration, so we will have dCA divided by dt, and this is the rate Ra. So, to determine the time to achieve a specified conversion x, we will have that dt is equal to Na0 times dx divided by minus Ra times the volume B. This equation is now integrated with the limits that at time t equals 0, the conversion x is equal to 0. And carry out the integration, we obtain the time necessary to achieve a conversion x in a batch reactor. So the time t is equal to Na0, the integral from 0 to x of the x divided by minus Ra times B. And this equation is the integral form of the design equation for a batch reactor.